Um, Last year also I was in the same conference, 24. There I talked about Gen AI. Gen AI, how it is disrupting VLSI chip design. So today you may be thinking I came with another jargon, but actually it is not. This is completely different one. There's something called Agentic AI which is coming up. Now we'll talk about what is the difference, why it is required, how is it disrupting silicon design. That's what we'll talk about today. I think a lot of automation was talked about. This is more about autonomy, which we'll see what is that autonomy, why we need, how is it changing the landscape of the design cycle. So that is the objective of today's presentation. And I will also talk about what Wipro is doing and what we have done so far, and how it is disrupting the entire cycle. So before we do that, I will talk about, take a minute or two on who are we and what we do today in silicon space. We are about 4,000 engineers in silicon design space, out of which 2,000 spec to GDS2 silicon engineers pure, around 1,200 to 1,300 embedded software, plus 500 to 600 system design, actual board design. So as you can see, we have built the entire skill set of anywhere from spec to silicon to embedded software to board design. And we can deliver the products to the customers. So we are enhancing even a little bit of packaging, manufacturing, assembly, test, and all those things. So tomorrow we may be able to, the objective is to provide the end devices, not just design, to our end customers. That is our immediate goal. So we are working towards that, hence we are growing. Hence we are looking for world-class teams who can deliver the devices, not just design. Okay, it's not just doing up to GDS2, but manufacturing, packaging, assembly, test, and everything. We do silicon design today for customers, consumer, mobile, handheld, AR, VR, AI/ML, you can name it, automotive. We have been doing silicon designs. We taped out at least so far 250 designs from our group, and about 500 system designs we have done so far. So that is our experience, and we have done tape outs up to 3 nanometer designs. 5 nanometer we already done, 3 is ongoing. So that is our experience, and 2 is also ongoing. That's our experience on the process node level. And needless to say, we have been there in the silicon design space for past 30 plus years. And we are recognized by all the industry leaders, such as Everest and Zinnov and all those things. So this is our overall credibility and credentials of our group. Then, on the AI space, I think in the last time also I talked about a little bit about this, but I will just recap this a little bit. We have heavily invested, Wipro has heavily invested into AI platform, a platform called AI 360. So this platform enables any type of LLM tuning, any type of application, any type of, it could be IT application, it could be business transformation application, it could be either edge device applications, it could be even for different industrial verticals. So it's a huge investment Wipro has done, and we have at least have around 1,200 different service offerings on AI basis for various segments, various applications and whatnot. So this is the platform which was created, and various customers have been using this platform for various applications which are mentioned here. Specific interest to us, VLSI, we will look at it today. First thing, on the VLSI space, where are we today? Why do we need something different? Right? Are we okay with today what we are doing? No, we are not. So today, all of you know, we are talking about 7 nanometer is kind of, I would say matured. 5 matured. 3 and 2 is the current trend. And then everybody want to pack more and more. onto the same die. Now we have reached a point where the die size has gone up to 500, 600 mm square. We can't even manufacture beyond that. Then we have gone for chiplets. So the complexities are exponentially growing, the expectations are exponentially growing. Manual ways of working is no longer going to take us anywhere. I can keep doing floor plan, I can keep doing, see, especially two areas in the chip design space are tool intensive, manual intensive, where you'll have to iterate many times. Physical design, one thing, for sure, and DV to some extent, I would say, but physical design mainly is tool dominant. Can we keep doing the same thing? Whatever we are doing now? No, we can't. Because how many chiplets will manually keep doing? How many months it will take? How many years it will take? There is a lot of time to market pressure. We can't afford to take years. Previously, yeah, it was 2-year cycle, 3-year cycle, it's okay. No, today it's not okay. So there's expectation of the market. And do we have enough skill set, right skill set, to do all the chipsets from grounds up manually? Probably the answer is no. The supply versus demand, there's a gap. The supply is low and the demand is too high. And traditional tools, are they okay? Maybe today they are okay, but they're not in the long run. Suppose if I have to scale up multiple levels of exponential growth in terms of number of devices I do manually, these tools are not good enough. Today, I'm sure most of you agree, most of the physical designer's job is to get the work done from the tool. Do workarounds and get it done somehow. So those things have to go. That cannot stay. And that is where we're talking about Gen AI, we are talking about Agentic AI now. I will clearly tell you in simple terms what is Gen AI, what is Agentic AI, and why both are required. But this is the current situation. We need something different. That much all of us agree. Now, what is Agentic AI? First, I will talk about a simple terms about Gen AI and Agentic AI, and then the difference we'll understand why we need this. Gen AI, simple terms, all of you would have used it, some form or the other. It's like a co-pilot. You ask them a question, it'll give you an answer. In the text form, video form, in any form, audio form. But there is something else. For example, there is an autonomous vehicle running. There I can't use Gen AI. Autonomous vehicle need, for example, it should take some input. It should process. It should take some actions basis that. That means it's a goal-based output. See, for example, in Gen AI, it generates output, it hands over the user. It doesn't validate what it has given. It doesn't take any action on the output per se. But that is not what is going to be useful. For example, think about, can I apply Gen AI to autonomous vehicle? No, I cannot. In autonomous vehicle, you have to take actions. Output is an action. Take some inputs, process it, and take some action. Like for example, you have some sensors, you have some processing engine, you have some actuators. Basis the sensor inputs, process, and then take the action. So the difference here is that it is a goal-based output. It is not just I'm asking a question and I'm getting an output. So that is the fundamental difference between Gen AI and Agentic AI. In the context of VLSI, we'll talk about it. Very soon I'll show you how complex the front end itself will be and what it means for the Agentic AI. I hope it is clear on the Gen AI and Agentic AI difference. Again, just to repeat one more time, Agentic AI is the one which is goal-based. The output of that will come as a goal-based and there will be multiple agents which actually interact with each other. Whereas Gen AI is simply like, I'm asking a prompt, a question, and I'm getting a response back, which is unvalidated response. So now, before getting further into Agentic AI, what it is for VLSI, where all it will impact? All areas, all. Be it front-end design, verification, physical design, DFT, post-silicon validation, you name it, it does. Now, in which way it does, we will see that. For example, physical design, you take an example. Now, floor plan, placement, routing, congestion control, timing. There are many, many constraints on which the actual physical design work has to be done. Manually, it's like beyond, uh, one's comprehension that how many iterations one can think manually. Whereas the machine is a machine. It has innumerable number of options, take the feedback loops, keep correcting it. So that is the difference with the agentic AI. So that is just one example, but it will impact all the areas. That's what I would like to say first. Let us take one example which is easy to understand. All of us work on the coding, right? RTL code, which is the starting of the design. Most of us will have a notion that it is as simple as just simply write a Verilog code, take it through some static checks, and do some synthesis, and we are done. No, that is not an efficient way of working, even otherwise today. Forget about AI, Gen AI, Agentic AI, and all these things. If you really look at it, the actual efficient way of working would look something like this. Today, let us not worry about agents. Let us say there is one person, design agent. That means there is an RTL designer sitting here. And there is one integration guy sitting here. And there is one QA, that means static checks guy sitting here. And one learning agent. This could be one of them also, or there could be another person. That means today also, if I have to write a code, I may write code, I integrate, there will be static checks, there could be some feedback, corrections happens, and this goes on in loops. So, and the learning also has to happen basis what you have seen as an issue. So that is what this learning agent is. So ideally speaking, if you really put together all these things, these many backs and forths will happen today. But most of us don't do that. It will go from generation, integration, static checks. It's like a forward flow. That is where some of the mistakes what we do will keep repeating. Either if not in this project, elsewhere. So that is because we are looking at this as an individual project by project basis, and then the learning of that one project going to another project is a manual process. Somebody has to really manually explain that. So this agentic AI is nothing but, you see, each one is sitting on the agent. This agent is nothing but a different LLM, large language model, or SLM, whatever we can call it, doesn't matter. It's a model. So these are all different models doing different jobs. One is doing RTL generation job, one is doing integration job, and so on, all these different ones. And then there is one orchestration agent which will actually route all the data between all of them. Now you can imagine, it's not like a co-pilot, I ask one question, I get an answer back. It's not like that. As these agents, they are doing their job and they're coordinating, the output of that goes to another agent. And that's getting validated there. The feedback goes there. For example, it comes from here to here, and then anything is there, the feedback can goes back. As you can see here, feedback. So, in this process, what is happening? Each agent is doing its job and giving the feedback to the next agent. That agent is learning on basis of what it has learned from the previous agent. As you can see here, this entire thing is built up as end goal basis. What is my end goal? I should have a clean code, I should have a synthesizable code, I should have a code with so-and-so power, so-and-so area, and so on. So those are the goals user will define. And the agents will take care of their individual jobs. And finally, you are getting an output which is goal-oriented, as opposed to just asking something and I get some output. So this is where the agentic AI coming into picture, more so from the wording of different agents sitting and doing the job and coordinating among themselves. Now you ask me whether this is future or now. It's already there, now. It is now and it is real and it is there. And it will only further improve because there are a lot of things which ideally need to be, like for example, we are trying to improvising these feedback loops. It's a little complex because as you can see here, within the simple task of RTL generation, integration, and static checks, there are so many loops which is ideally supposed to happen. Okay? We're trying to incorporate all of them, but it is already there, and this is going to further improve. This will kind of validate a lot of this time it takes for you to develop any subsystem, any SOC, doesn't matter, IP. So it's going to significantly reduce this time. I will just simply skip other parts because it's going to take time. For example, DV. We have also created this. These are not concepts. This is our platform. This is our framework. So we have created a DV agents which can do TB, test bench generation. It can write test cases. It can do assertion writing. It can do coverage analysis, coverage improvements. This is yet another Agentic AI for DV. So one for, I showed about the RTL, one for DV. So this is also in flight. We have a POCs already running with us. And I will try to skip faster. So then DFT. DFT, there are multiple options, possibilities. One is in the initial phases of, I would say, coverage improvements, ideas. Like we are doing netlist. I mean, you are inserting the flops, right? Scan flops into the netlist. Coverage. And then debug. Debug is one of the main aspects. It can do an automatic debug of all these things. So ATPG and GLS debug is one area. Main area is that tester time reduction. Because test vectors ultimately will decide test time. Test time is nothing but the cost of the device. So all these agents will work together and give you the right set of ATPG vectors. That is the objective behind this. With the minimal set of vectors, you get the best coverage. That is the goal, which is given to the Agentic AI engine. Physical design also similar way, I didn't put that. There also PPA, I can define, okay, this is my floor plan area, that's it. This is the power number target for you. Go on agents, figure out. And then show me the best floor plan. And I will show you what kind of efficiency is expected out of this. It will be really shocking, actually. We'll talk about that. So now you may ask, again, I said, is it future, long time? No, after 10 years, this research will evolve? No. Prediction, and it is a data-based. By 2027, we are not very far. 90% of the chipsets of the complex chipsets, I'm not talking about simple ones like automotive ones and this, 90% of them will be designed by Agentic AI agents. 90%, not 10%, 20%. Okay, so that is the projection, and we must be ready for that. We will also talk about what industry has to do, what EDA companies have to do, what academic institutions have to do. Everybody has to do. It's not like one job and it's not like one type. So that's one thing. So all this, a lot of collaboration also required. So there are many concerns of, oh, what will happen to my IP? Is it contaminated? Or is it getting into your model? So there are issues. We are talking to customers. There's no issue. There's a public cloud. There's a private cloud. You can manage all of that. Your LLM is fine-tuned for you, and then it will do your job. You don't have to worry about, someone else's data getting into mine and my data getting into someone else. Okay? So, and interestingly, there is something called AI EDA. If you just Google it, you'll get it in paper in IEEE. This is an open platform, which is very promising platform. And I believe it will have a lot of impact on at least a lot of the smaller companies also to adopt, because it's a big time research. And also you need big time infra, big time compute, everything requirement to even experiment all these things. So that is very promising platform, it looks for me, AI. Ultimately, these things, in my opinion, has to be democratized. It has to be accessible to all companies and all, however small they are and big they are. Today, it is very specialized. It is kind of, only with few companies, but I'm sure going forward with the cloud enablement and with companies coming out and trying to share the data, this is bound to happen. So this is the industry trend and benchmark point of view. Now, here is the most interesting part. What is the business impact? Okay, fine, you're saying something, Agentic AI and all that. The expectation is the 30 to 50% is expected cycle time reduction. If I'm doing tape out in 15 months today, by 2027, don't be surprised that the customer will be asking for 7 months, 8 months. Today, we have already been asked by our customers. It is not something which is futuristic. But the only thing is we are talking about 25%, 30%, but the expectation is right here, 30 to 50%. And they're also expecting that it should be first for silicon success, which means they're expecting the bug rate you should catch much ahead. How? Manually, is it possible? No, it's not possible. And they're also expecting that it is much more super efficient. Test time is reduced to the hilt, and then you're not going to spend even a millisecond extra, so it's a cost. So all these constraints are coming to us, and improve design quality, shrink the timeline and improve the quality. Look at the expectations. So all these expectations, today we sign some of the deals with our customers. We actually put these efficiency numbers into the SOW. You can imagine why I'm saying, because this becomes a norm. It's no longer, good to have or optional. It's not a differentiation anymore. It is a must. It is there today. Some ethical things and certain technical considerations we need to have. I talked about briefly. Today, there are some concerns about IP contamination, IP training, especially from training point of view. I think we are settling down. We are telling our customers, we are explaining how the things are, and they are also understanding. So that was one of the concern. And there are a few other things like explainability and verification. This is a little bit technical about the models, but there are other factors like explainabilities need to be considered. End of the day, human in loop. All of us need to be skilled, and we have to reskill ourselves on how to get this done, as you also were talking about system. So if you have an understanding of that, lower level, you look at it this way, right? Your level of abstraction is going up. You don't have to really code a multiplier divider. It's all done. So that is the level it is. So we need to upskill ourselves into how to utilize, or something it's called prompt engineering, and agentic AI, we call it as a different terminology, but we need to see how to extract what we want from these engines. That becomes more. Plus, fine-tuning the overall output it is generated to make it error-free. And some level of fine-tuning we all will have to get into. What kind of data it understands, how to fine-tune. So all these things you will see a skill set shift over next 2 to 3 years from a pure manual work to it'll keep shifting. So future directions. I see that analog is one space, analog and mixed signal, which has not been matured yet. So that is one thing which definitely I see as one of the area where future trends are. And today, customers are a little afraid about putting it in the public cloud. The cloud deployment will make it more democratized across the companies. That's going to happen in future directions. And last but not the least, there are few other techniques coming up, something called symbolic reasoning, something called reinforced learning. I'll not get into any of details of those, but AI engine per itself, we are also trying to improvise the algorithms and all that. That's another part. So these are the future trends. And now what we need from all of us as the community of the silicon design, there is no way we can stop this evolution. It has done, it has started, already happened. Now, we need to be preparing ourselves. All the stakeholders should, I would share the knowledge across each other, and certain models, not the sensitive data. I think that is really necessary, I feel, because it's happening in pockets right now. Companies are working in bits and pieces. When we talk to our customers, they say, you have a solution end to end. So, which means it is running in different pockets. All this need to be integrated somehow. And EDA companies also have to step up in doing so Today, they are also having pointed solutions. So hence, every company is they're building their own. But they're building, they will not stop. So, and I think all these things have to be brought into education itself in the beginning, like engineering and other degrees itself, we have to bring in all these things. It becomes some kind of mandatory now. And of course, investments. Every company is investing, so as we are investing, and heavy investments are required, and definitely this is a mandatory thing. And research is going on anyway in parallel on the algorithms, on the models, that will continue. Definitely with all these things, it is not too far, just another 2-3 years. So that's all I have today from my side.